This is actually a continuation of 3NF. The next normal form we need to study is BCNF, or it is the short for Boyce-Codd normal form. Actually, this BCNF is an extension of 3NF, and for university usually they ask a comparison between BCNF and 3NF. So before we go to BCNF, it is also known as 3.5NF. It is actually an extension of 3NF. So before we try to understand BCNF, let's just have a quick recap of what 3NF was, or third normal form was. So for a table to or a relation to be in 3NF, we saw that it should satisfy 2NF, that is, there should not be any partial dependency. So once we have converted a table into 2NF, for to check 3, like a table should be in 2NF to be in 3NF. So it is by default, if it is in 3NF, it should have satisfied 2NF. Then the next property that comes in 3NF is transitive functional dependency of non-prime attribute on any superkey should be removed. That is, we saw that transitive dependencies should not be there from key to any non-prime attribute. So in order to understand BCNF, just go back and listen to the 3NF if 3NF is not clear to you, because it is required to understand BCNF. So we have, in order to understand BCNF, we have got another definition for 3NF, like consider a dependency X gives A. If you have a dependency X gives A, the dependency does not violate 3NF if either, it's like an or, either X is the super key or the key, or A is a prime attribute. Even if A turns out to be a prime attribute, then also that dependency does not violate 3NF. Why? Because the transitive, this X gives a X is a super key. I hope that you understood that X should be a super key. Now if X is not a super key, at least A should be a prime attribute. Then it satisfies 3NF. This A should be a prime attribute arises from this condition, that transitive dependency on non-prime attribute should be removed. So if the dependency is coming from a prime attribute, it's okay. Let's look at using an example. First consider this example, then we'll go to BCNF. Consider a relation R with attributes P, Q, R, S, T, and there is a relation like functional dependency like R gives P. R gives P. Now this table would be satisfying 3NF, because this, imagine this is the only dependency left. So R gives P does not violate 3NF because this R is not the super key, but P is a prime attribute. Now what was a prime attribute? An attribute is a prime attribute if it is part of the candidate key. Now P is a key, so P would be a prime attribute. So the RHS of this functional dependency turns out to be a prime attribute. So this does not violate 3NF. So this table is in 3NF. Now let's see what BCNF provides as an extension to 3NF. So in 3NF, if you have a relation like X gives A, this X gives A is taken as a common dependency. Here it was R gives P in place of X gives A. So if you have a dependency like X gives A, either X should be a super key, or you have an option, either X should be a super key or A can be a prime attribute. Either of this condition, if it is met, it satisfies 3NF. But when we come to BCNF, it clearly states that in X gives A, X should be the super key. The second condition should not be there. X should be the super key. If there is a dependency like X gives A, X should be the super key. Only then we can say that that table satisfies BCNF. So that is the difference between 3NF and BCNF. In 3NF, either of these two conditions, if it satisfies, it is in 3NF. But in order to be in BCNF, only the first condition is taken into consideration. X should be the super key. So we also say the question can be like, why is BCNF more strict when compared to 3NF? Because in 3NF, either of these two conditions can be satisfied, but in BCNF, this particular condition alone, if it satisfies, then only we can say it is in BCNF. So BCNF is termed to be more stricter than 3NF. So now if this was the relation, this satisfies 3NF, but this does not satisfy BCNF because R is not the super key. Now to convert this into BCNF, we can split this into two relations. Like we can remove this R gives P as a second relation and make R the primary key in that relation, and we can keep the other relation, that is PQST, as a single relation. So if we split this into two, now these two tables satisfy BCNF. So if a question is asked, like you are asked to compare BCNF and 3NF, you should be explaining what 3NF is, what BCNF is, what is the difference between these two, and you can use a simple example like this, showing that this relation is satisfies 3NF but does not satisfy BCNF, and in order to convert it into BCNF, this is the answer. So this is a short explanation for that particular question. Now we'll try to understand the relevance of BCNF using a more real world example. So exam wise, in order to compare 3NF and BCNF explanation, this much is enough for a simple 3 to 5 mark question. So those who are looking for just exam wise content, you may actually stop here also. But if you really want to understand why BCNF is required over 3NF, you may just continue watching the video. And we will take this example, we will consider an example from scratch, a real world example from scratch, and first we will convert it into 2NF, then 3NF, then BCNF. We will just have a flow of that. So you may also stop the video if you are just concerned exam wise, but I appreciate continuing to understand this example, and this example is also briefed in your note. So consider the schema, like a country has decided to have a database for all the property, land property sales it is going to conduct. So it is like if a particular property is for sale, it would be there in this database, and that each property would have a unique property ID. So that is taken as the key in this case. So each property would have a unique property ID. Now let's try to understand the next attribute. This county name, it's not country, it's county itself, because it's like in foreign countries the states are referred to as counties. So this county name and lot together forms another candidate key. It's like, imagine Kerala to be a county, Tamil Nadu to be another county. So within Kerala, we can have lot numbers 1, 2, 3, 4, 5, 6 and so on. Within Tamil Nadu, again we can have lot numbers 1, 2, 3, 4, 5, 6, 7, 8, so on. So this lot number as it is not unique, or this county name as it is won't be unique, because there will be lot many Kerala's over here, there will be lot many Tamil Nadu's over here, but Kerala 1, Kerala 2 or Tamil Nadu 5, Tamil Nadu 3, this combination would be unique. So this is another candidate key that we can have. But since this is the minimal key, we take this to be the primary key, but this county name and lot together forms the candidate key. Understand that also. The next is like area. How much area is for sale, what is the price, the tax rate. Now let's try to understand what the dependencies are. The functional dependencies given is like property ID should be, all the other attributes should depend on property ID because that is the key. Then we have another dependency like county name and lot gives all other attributes, since this is also a candidate key. Let's try to understand third dependency. County name decides the tax rate. It's like the tax rate would be dependent on the county. Like for Kerala, we'll be having a particular tax percentage. For Tamil Nadu, we'll be having another particular tax percentage, so on. And area depends on price. Now this can be a confusing dependency for you. Just try to understand in this context. It's just taken for this particular example. It's like if it is 1 acre of land, this would be the price. If it is 0.5 acres of land, this would be the price. It's not like in our concept, it's like if the land is in MG Road and if it is 5 cents, it is more worthier than maybe a 1 acre in Arakundam. So it's not like that. It's like if it is 0.5 cents, this is the price. If it is 1 acre, this is the price. So it is irrespective of the location where it is located. What is the area? The price is dependent on the area. For 1 cent, this is the price. 2 cent, this is the price. So we have such a dependency also. Just imagine there's such a dependency, and let's try to understand how we can overcome or decompose this example. So there are 4 dependencies as of now. So let's first take this. As you can see, it would be in 1NF because the domain attributes are single. Now, but let's now see whether it violates 2NF. Now 2NF, the definition was like there should not be any partial dependency. So the first FD1 and FD2 does not violate 2NF. Let's consider FD3. FD3, its county name gives tax rate. Now that is a partial dependency. Why? Because tax rate is partially dependent on the candidate key. If it was dependent on county name and lot together, it would not it would have been a full dependency. But since it depends only on county name and lot together forms the candidate key, so since the tax rate depends only on county name, it's a partial dependency. Now you might be confused, like partial dependency is taken not only on the primary key but also on the candidate key also it is considered. In this case, tax rate depends partially on this candidate key because only it depends on one of the attributes of the candidate key. So this county name gives tax rate violates 2NF and we should remove that. Area gives price does not actually violate 2NF. Why? Because area is not part of the candidate key. So only if there is a partial dependency on the candidate key, it is a violation of 2NF. So area gives price is not a violation of 2NF. So in order to remove the 2NF violation, that is county name gives tax rate, this schema is divided into 2. This schema name was lots and lots is divided into lots 1 and lots 2. We can see county name gives tax rate, that part is made another relation and county name would be the primary key for that. This should be clear if you have followed the problems for normalization. What would be the content of this? Property ID, county name, lot, area and price. The another mistake I have seen students make is when they decompose this, they just remove county name and tax rate. They remove these two attributes into the and make this relation. Actually, county name should exist in this relation. Only the y x gives by y part or the right hand side should be removed from that. The other one, county name, should exist in the original relation. Keep that in mind. So this is the answer for 2NF. So we have two relations. Now let's see whether they are in 3NF. Now you may see that this particular relation is not in 3NF. Why? Because there is partial dependency coming. Or area gives price. Just take the example, area gives price. Either area should be a super key or price should be a prime attribute. That's the definition of 3NF. Area gives price in that either area should have been a super key or price should be a prime attribute. Neither is satisfied. So this violates 3NF. So we can have a separate table for that. So this table is again divided into area gives price. We create a separate table for that functional dependency, making area the primary key. Area, the left hand side, is kept as it is in the relation. So this is the answer after 3NF. So try to understand this also. So till now there was lots. After 2NF we had two tables, lots 1 and lots 2. Lots 1 violated 3NF, so we convert again split it into lots 1A, lots 1B. This was lots 1A, this is lots 1B. Hope it is clear till now. Now let's try to explain this example a bit more to bring in the case of Bcnf. Okay, just try to listen carefully to this example. Now imagine there are thousands or 1 lakh of properties that are for sale, and so consider this relation. Let's take lots 1A. Property ID is there, county name is there, lot number is there, area is there, and there are 1 lakh properties for sale or thousands of properties for sale. But there is a restriction, like all the properties are from 2 counties, or just all the just assume this example we are using such assuming such an example just to understand Bcnf. So just imagine all the properties are from 2 counties, DeKalb and Fulton. All the properties are from these two counties. And there's another restriction. If it is from DeKalb, the size of the property that can be for sale is 0.5, 0.6, 0.7, 0.7, 0.8, 0.9 or 1 acres. Like if a property is for sale from DeKalb, this will be the size denominations of area. This would be the area of the land that is for sale. They have to sell it like this. Either it can be 0.5, 0.6, 0.7 up to 1 acres. So, and if it is from Fulton, the property size is like restricted to 1.1, 1.2, 1.3, so on up to 2.2 acres, 2 acres. So 1.1 acre to 2 acres. So if I am telling you there is a land of 0.8 acres for sale, you can easily know it is from DeKalb because that denomination is for DeKalb. And if I say there is a 1.5 acre land for sale, you can automatically know it is from Fulton. So now there is an additional dependency coming up, like area depends on county name. So if you give the area, you can know the county name. That is a dependency over here. If I say 1.5 acres is the area, you can easily say the county is Fulton. So there's an additional functional dependency that comes over this table if we consider this particular case. So the dependency would be area gives county name. Hope you understood that. Area gives county name. Now just imagine or think for a moment and say whether this FD5 violates 3NF. Would it violate 3NF? It doesn't violate 3NF. Why? Because area gives county name. What is the condition for 3NF? Either area should have been a super key or this county name should be a prime attribute. In this case, county name is a prime attribute. Why? Because county name and lot together forms the candidate key. So since county name is a part of candidate key, it is a prime attribute. So in this, area is not a super key, but county name turns out to be a prime attribute. So this does not violate 3NF. So this is okay, like it is not violating 3NF, but this won't be an efficient table. Can you say why? Just imagine, like we had assumed that there are 1 lakh plots for sale. So but they are from just two counties, and if it is from DeKalb, these are the denominations. If it is from Fulton, these are the denominations. So there are just two counties, and how many denominations are possible? Like 1, 2, 3, 4, 5, 6 from here, 10 from here. So there are only 16 values that area can take. That is 0.5 to 2 acres. There are only 16 values area can take. And there are just two counties over here. So this area, it should just occupy 16 rows. But if we are keeping a table like this and there are 1 lakh properties for sale, there would have been 1 lakh rows with a lot of repetitions. Like only 16 values are there in area, but 1 lakh row values should be there. Only 2 values are there in county, but 1 lakh times the things are getting repeated. The 16 values would be repeated n number of times simply. It requires a bit of thinking to understand that. So this just now 3NF, by going up to 3NF, this disadvantage is not removed. Like if there are 1 lakh properties and this dependency still holds, then this is the schema, and only 16 values are possible for area, things are getting repeated a lot many times. So 3NF doesn't provide an optimized solution in this case. But what if we go for the next normal form, Bcnf? According to Bcnf, area gives county name. In that, area should be the super key. You don't have the other option of county name being the prime attribute. That was there only in 3NF. So for this area gives county name, to satisfy Bcnf, area should be a primary super key, sorry, or primary key or candidate key. Okay, so area should be a candidate key, which is not true in this case. So in order to make this into Bcnf, we remove this dependency, that is area gives county name, into a separate relation with area as the key. since area has unique value starting from 0.1, 0.5 to 2 acres, it is okay. The corresponding county name would be listed. And in this table, property ID, area and lot is listed. Now, please be careful when you remove the dependency area gives county name. Always remember the left hand side of the functional dependency should be left in the original relation. The right hand side is removed with this, that dependency area and county name. Now this is more efficient. Why? Because as you can see, the county name is removed from this. In this, county name and area. So if there are 1 lakh properties, there are just 2 county names. They are repeated like 50,000 each on an average. But in this case, there will be 16 areas and only 16 rows for county names in place of that 1 lakh rows. So that is the advantage we are having by going for BCNF. Hope the example is clear to you. So this actually doesn't violate 3NF but violates BCNF. So by going for the next higher normal form BCNF, we have made or optimized the table in a more better manner. It is good if you understood this example, or like if it is for exam it's 3NF and BCNF is asked, you can explain using such a simple example and compare those two. And for exam, one more thing you need to notice, if a relation is given and you are asked to convert it into the highest normal form possible. So the highest normal form possible that you have learned is BCNF. It goes like 1, 2, 3, then BCNF. So if you are asked to convert the relation into the highest normal form possible, you should be seeing that the final answer satisfies BCNF. Actually, the normal forms, there are normal forms 4NF, 5NF, but that is not there in your syllabus. Your syllabus ends with BCNF. So if such a question comes, you should be, and you are asked like try to convert it into the highest normal form possible, you should be converting it up to BCNF. So hope that is clear to you. Thank you.